So let's talk a little about hyperspaces. There are only two kinds of, a hyperspace, by the way, just a term for a space of more than 3 dimensions. You and I are familiar with two-dimensional space. It's called a scratch pad, or a photograph or a piece of paper is a two-dimensional representation of something, typically. Three-dimensional space we're familiar with because we live in it, and we also build models in 3 dimensions. We probably have a vague feeling of a 4th dimension called time. We don't get too comfortable with that unless you've done some special study, but we sort of acknowledge that reluctantly. Hyperspaces, frankly, is just the term used to study spaces of more than 3 dimensions. And we discover there's only 2 kinds of people that can really relate to hyperspaces. And that's mathematicians with special training and small children. Okay? Because they haven't, their prejudice has been blindfolded, so to speak. Now, the one book that is second to the Bible in its publication, all of us know the Bible is the most popular book in the history of man, but the second to that would be Euclid. And that's where most of us have been taught in school. And most of us, when we went to school, had trigonometry or plane geometry, same subject in a sense. We all know that a triangle, if you add up the angles of a triangle, adds up to how much? Anyone? 180 degrees, you betcha. So if I have a 30, 60, 90, it adds up 180. If I have a 45, 45, 90, in fact, any triangle, if I add up the angles, it would add up to 180. Suppose, though, that my partner and I went out to a large field here, and we very carefully laid out with the transit a very large triangle, and when we got back with our figures, we added up the 3 angles, and it added up to more than 180 degrees. What would you conclude? That we'd messed up, huh? No, what have we encountered? Anyone? The curvature of the earth, exactly. See, if you take a course in navigation, one of the things that you'll have to get some background in is spherical trigonometry, where you can have a triangle with 90 degrees in each corner. And so, see, this little rule that we all learned, that a triangle, by implication, a plane triangle, a flat plane, adds up to 180 degrees, that's only true for a universe of 2 dimensions. So when you find that rule violated, it's a hint that you've encountered an additional dimension. And Dr. Einstein made history with that insight, because he was grappling, of course, with the nature of space, and he realized that length, mass, velocity, and time are relative to the velocity of an observer. In 1915, he generalized that, basically discovered that there's no distinction between time and space. And perhaps the most important thing from the general theory of relativity, we won't get in the math, of course, but is to realize that time itself is a physical property. You and I do not live in 3 dimensions. We live in at least 4. In fact, we now discover much more than that. But this idea that Einstein recognized as he grappled with the properties of space, that there's an additional dimension required, and he went to 4 dimensions to resolve the time issue. And his theory of relativity has been confirmed over 12 different methods to over 14 decimals. So it's no longer really a theory. It's well-accepted basis in certain fields of science. So when we need to go beyond Euclid, which of course deals just with 3 dimensions. And in June 10th of 1854, the most important lecture in mathematics was given by George Riemann. He invented a thing called metric tensors. And that tool that he developed proves to be one of the most profound tools in advanced physics. And it took over 50 years, in fact over 60 years, for Dr. Einstein to use that tool to develop his 4-dimensional space-time. And it's too bad that Einstein went to his death frustrated by not being able to solve certain problems, which if he had applied the technique going to 5 or more dimensions, they would have yielded. It took his successors to do that. Because in 1953, Kaluza and Klein both developed more than 4-dimensional models which integrated light and supergravity in a model. In 1963, 10 years later, Yang and Mills both developed what they call Yang-Mills fields, which reconcile electromagnetic and nuclear forces. That physicists are pursuing some way to integrate all that we know about the physical universe into a common model. And so as early as 1984, and it's still a current conjecture because there's still problems with it, But scientists now generally believe that you and I live not in 3 or 4 or 5, but in 10 dimensions. And if you read in this area, you'll encounter superstrings and such, and I won't get, we have briefing packs on this for those that want to get into it more. The point being, we need to understand that the 3 dimensions you and I are familiar with are not all there is. There's more. Let's imagine you and I can't move up. It'd be futile for me to try to communicate 4, 5, 6 dimensions to us together without having more mathematical tools. But what we can do is we can go the other way, and it may stretch our horizons here a little bit. You and I are 3-dimensional beings. Let's imagine a 2-dimensional world. That would be like a large tabletop or a large flat plane. Now, let's imagine that 2-dimensional world populated by 2-dimensional people. You and I could come along and poke our finger through the plane of their existence. And what would they see? They would see a circle. They'd only see that which they could relate to in their universe. But if we as a 3-dimensional being are putting our finger through that 2-dimensional universe to the 2-dimensional people in the 2-dimensional universe, they would simply see a circle. Well, in fact, let's imagine that a ball fell through that 2-dimensional universe. To the 2-dimensional observer in that 2-dimensional universe, he'd see from nothing to a point. It'd grow to a large circle, and then it would shrink back to a point and disappear. He wouldn't be able to relate to what happened because he doesn't have the insight of that 3rd dimension. You with me so far? Now, if you had some other kind of a shape, say a tumbling cube, it also would go through, and it would take odd shapes as it passed through and then disappear. So one of the problems we have, suppose you and I are going to try to communicate a 3-dimensional object to that 2-dimensional world. How would we go about it? Well, there's a couple of ways. One would be to do what an architect would call projection. For example, if we had a cube, we could, in effect, shine a light that would give you a profile of that in 2 dimensions. And you discover very quickly that that works, but it's not too useful in letting the 2-dimensional person understand a 3-dimensional cube. So there's another way you could do it. You could take a 3-dimensional cube and you could unravel it. You could take it and just unfold it and lay it out, and that would be a way to communicate to this 2-dimensional person what this 3-dimensional cube is like. But you'd quickly discover as you tried to do that, his understanding is likely to be incomplete. You say, Chuck, what's all this got to do with anything? Well, let's talk about a 4-dimensional cube. That's called in mathematics a Hinton cube, and there are such things. The only place I know of it, it's called a tesseract. That's an unraveled Hinton cube. This is a 4-dimensional cube unraveled into 3 dimensions. You say, gee, what good is that? There's only one place I know of where this has actually been used constructively. And amazingly enough, it was by Salvador Dali. I never realized what a sophisticated mathematician he was, but in his Corpus Christi painting, he actually has Christ on a 4-dimensional cube as a cross, implying his mastery over time as well as space. And I imagine there's probably not one observer in 100 that really understands the sophistication that Salvador Dali was demonstrating by this piece of abstract art. But that's a Hinton cube or a tesseract, and that's the. But anyway, let's get back to hyperspaces then. The main point I want to get across: you and I live in 3 spatial dimensions, and that time is a physical property. That's very important to us in our ministry because we know that the Bible is an integrated message. 66 books penned by 40 guys over thousands of years. And yet it's integrated, and not just thematically. The very design of the text itself evidences integration. But what's mysterious about that integration also implies that the origin of that message is from outside the dimensionality of time because of the nature of its structure, its use of writing history before it happens, and so forth. So that's very important. Now, in particle physics, they talk about 10-dimensional strings as the nature of our universe. What fascinates me about that is that that's exactly what 2 Hebrew scholars back in the 12th century, predicted just from their study of Genesis 1, is that we live in 10 dimensions, 4 dimensions are knowable, and 6 are not knowable, to use their jargon. But